Okay, so we're going to start by talking about sequences. And a sequence is just a list of numbers that may or may not follow a pattern. Whereas, which we'll talk about later, a series is a list of numbers, but you're adding up all the terms. So where a sequence is going to be something, whereas a sequence is, or a series is going to be, you add them all up. That's kind of the main difference. And I feel like they could have picked better names that didn't sound quite so much the same. Usually, often people say sequences and sums to differentiate between them, right? A sum, very obviously, you're adding things together because sum is the word for adding things together. Whereas series is less explicitly, I feel like, telling us what is actually going on there. So let's look at some sequences. And we'll start by asking if they converge or diverge. So let's say A sub n is the sequence given by the formula 2n over n plus 1. Now, people like to ask various things about sequences. One thing we could ask is, what are the first 5 terms? So first 5 terms. Sometimes they'll tell you where to start. If they don't, well, it kind of actually depends. Usually you start with n equals 1, but sometimes you start with n equals 0, or wherever they tell you to. No one has said anything about where to start. So you typically want to assume that you're going to start n equals 1. Unless your teacher says to assume n equals 0. It's kind of either one of those is very standard. So it can be either one really. But I'm going to assume n equals 1 unless there's a good reason to assume n equals 0. So a sub 1 is going to be, it's just a function, right? We're just plugging in 1 for n. So I'm going to get 2 times 1 over 1 plus 1. 2 over 2 is 1. I don't think we really need to show all the work. A sub 2 is 4 over 3. A sub 3 is 6 over 4, which you could reduce, but I often don't reduce things when I'm writing them out because it kind of takes away from the pattern aspect of things. A sub 4. Here, at this point, we can see that the top is going to increase by 2 every time. The bottom is going to increase by 1 every time. So A sub 4 is 8 over 5. A sub 5 is 10 over 6, and so on. If I want to see if it converges or diverges, I'm really just asking what's the limit of the sequence as n goes to infinity. So converge or diverge is really asking the question, what's the limit as n goes to infinity of the sequence? If the limit exists, then we say that the sequence converges to that limit value. If the limit does not exist, we say that the sequence diverges. So I should say if the limit does not equal a real number, then I'll say more about that in just a minute. In this case, we're going to take the limit as n goes to infinity of 2n over n plus 1. And here's where we have to remember all of our limit rules. In this case, you could use a lot. You can do a lot of work, but you really don't have to do any work here. This is a rational function where the degree on top and the degree on the bottom are the same. So we know that the limit of a rational function as the variable goes to infinity is the quotient of the leading coefficients when the degrees are the same. So that's going to be 2 over 1, which is 2. You could also see this, right, if you wrote out a lot more terms, or like you could write out the, say, 1,000th term is 2,000 over 2,000 over 1,001, which is pretty close to 2, right? We can see that, oh yeah, as you let n get very, very large, the top is about twice as big as the bottom, so that the limit is getting closer and closer to 2. So I would probably just write that the limit was 2, but you could also say, if your teacher expected you to write more words, that the sequence a sub n equal to 2n over n plus 1 converges to 2. Writing this says the same information, just with different language or words. On the other hand, this sequence, a sub n equal to 2n squared over n plus 1, We could also write out some of the first terms. We get, let's see. So sometimes people just write out the sequence terms, right? I like to use a colon here and say, okay, my first term is going to be, let's see, 2 over 2, which is 1. And sometimes people like to write below it, that's my a sub 1. And then a sub 2 is going to be, let's see, 2 times 4 is 8 over 3. And then a sub 3 is going to be 2 times 3 squared is 2 times 9 is 18 over 4. And so on. And yes, there's a reason I'm writing it this way. I really like to emphasize that when we're talking about a sequence, we separate the terms by commas often, or we just write the formula for the sequence. And so the fourth term, a sub 4 would be 2 times 4 squared is 16 times 2 is 32 over 5. And the fifth term, a sub 5 would be something over 6. 2 times 5 squared is 50. Great. There's the first 5 terms. Normally, we don't do a lot of this, right? Like, it's good to be able to think about what the terms are going to be. And I should take it back a little bit. There are some sequences where we actually do this because there's no other way to really determine what we are converging or diverging to. A good example is a factorial in a sequence. But for ones like this, we often just kind of bypass and say, okay, what's the limit? Does it converge or diverge? Well, we take the limit as n goes to infinity of 2n squared over n plus 1. We can also recall from our previous work, well, there's a couple ways you could do this. You could either say the degree on top is larger, which means this thing doesn't have a limit, right? The numerator is getting bigger than the denominator. This is going to diverge to infinity. But you could also use L'Hopital's rule, right? L'Hopital's rule is in play. We totally could have used it here. We just didn't need to, but you could have taken the derivative of the top is 2, the derivative of the bottom is 1, and you get 2 over 1, which is 2, right? Because this is an infinity over infinity type. Here, it might make more sense to actually use it because, again, this is infinity over infinity. So we might use L'Hopital's rule and say, okay, well, I'm going to take the derivative of the top, which is 4n, and the derivative of the bottom, which is 1. And now I can see that, oh, I've got an infinity over a 1. That's going to be infinity. Now, I know I'm saying the limit is equal to infinity, but that's not a real number, right? Infinity is just a direction. So we don't say that the sequence, we do not say it converges to infinity because we don't, right? You're not getting closer. I mean, you're approaching infinity. You're getting larger and larger and larger, but you're not really ever getting close to infinity because you can't, because it just is it's the thing that's way out there, right? That we can't ever roll way out there, right? From left to right. It's the thing that's way out there that we can't ever actually get to. So we say that this sequence diverges. And you can just say it diverges, but typically, if a sequence or series specifically diverges to infinity or to negative infinity, we usually include that information because it is useful. A sequence can diverge to infinity. A sequence could diverge to negative infinity, right? If I put a negative sign, if this was a negative 2n squared up here, the sequence would diverge to negative infinity. And then sequences can diverge and not be going to any one particular thing. A couple examples of that. Often alternating sequences that go back and forth between two values. So here are 2 examples. This sequence, -1 to the n, and this sequence, -2 to the n. Both of these diverge. And both of these diverge in a way where you can't say anything else. So for this one, the terms, we start at n equals 1. We get -1 to the first, which is -1, and then -1 to the second, which is +1, and then -1 cubed, and then -1 fourth, right? We just keep going back and forth between 1 and -1. But we're not getting close to one specific value, right? Whereas, right, this one, right? Oh, not this one, sorry, the one I erased on this side, the numbers were getting closer and closer and closer to 2. These numbers are not getting closer and closer and closer to any specific number. so it diverges. But it's also not diverging by getting really infinitely large or really negatively infinitely large. Same deal here. This one kind of even more annoyingly, because the terms look like this. The first term, when n equals 1, you get -2. And then -2 squared is +4. And then -2 cubed is -8. And then +16, and then -32, and so on and so forth. And the problem is, it's getting bigger and bigger, but it keeps jumping back and forth between the positive and negative number. So it's really positively big and then negatively big, and then positively big and then negatively, and positive and negative, right? But we can't say it diverges to positive infinity because not all of the values are getting positively large, right? It keeps jumping back down to a negative value in between. So this one also just diverges. And that's all we can say. There are other ways of diverging as well. Oh yeah, let me give you one more good example. But most of the time, when you are divergent and it's not to some sort of infinity, it is often in an oscillatory way, meaning you're jumping back and forth between two different values. Another good example of this is, sure. Is the sequence a sub n equal to, let's make it fun. Oh, let's make it fun, sure. Sine of, now I have to now I'm like, what's the thing I'm looking for? Oh man, sorry, there's like an easy way to do this, but there's also, oh. Did I write 4 over 1 equals infinity over? Oh, I just erased it. I'm sorry, I just erased it. So Mariah, I did write that 2n squared over n plus 1 was an infinity over infinity type. But then I used L'Hopital's rule and got 4n over 1, which I don't think I wrote was an infinity over infinity. But yeah, both Mindy and Nida, sorry, I'm butchering your name, I know it. Both of them wrote, yes, L'Hopital's rule. So we were finding the limit of this. And we use L'Hopital's rule and took the limit as n goes to infinity. And the derivative of the top was 4n and the derivative of the bottom was 1. So I guess what I should really say is that we use the fact that it was an infinity over infinity type to justify our ability to use L'Hopital's rule to get this answer, which is no longer infinity over infinity. Just infinity over 1. Okay. Oh yeah, there was one other that I was trying to come up with that was going to be interesting, but now I've forgotten how to make it fun. Oh, I know what it is. That's not super exciting. Yeah, I thought I had a cool one, but I don't. I'm gonna skip it for now. I know what I'm thinking of, but it's kind of the limit as we go to 0, actually. Okay. So yeah, so this example I think is always worthwhile. Some more sequences. So a sub n equal to n squared over 2 to the n. And this is where it starts to become fairly useful to have a good idea of what things get bigger faster. So what do we think? Does the polynomial n to the second power thing get bigger faster? Or does the exponential 2 to the n thing get bigger faster? What do you guys think? Is it the top thing that gets bigger faster, or is it the bottom thing that gets bigger faster? I believe Rodrigo is correct. And typically, right, even the names, right, kind of say we are used to thinking about exponential things growing really fast. And it is definitely true that an exponential thing is always going to grow faster than a polynomial thing. To take the limit of this, as n goes to infinity, we definitely have to use L'Hopital's rule. Right, this is still an infinity over infinity type. So we're going to use L'Hopital's rule. We're expecting it to eventually be 0 because the denominator is the thing that is larger eventually. We use L'Hopital's rule. The derivative of n squared is 2n. The derivative of 2 to the n is 2 to the n times what? I know it's been a while. It's 2 to the n times natural log of 2, exactly. We still have an infinity over infinity type, right? 2 times infinity is infinity. 2 to the infinity times natural log of 2 is also infinity. So we do it again. So we use L'Hopital's rule one more time. Make the limit as n goes to infinity of 2 over the derivative of 2 to the n times a constant is the derivative of 2 to the n, which is 2 to the n times the natural log of 2 times the constant that was already there, which is the natural log of 2. And now we see that we have a constant divided by something that's infinitely large. That's going to go to 0. So this sequence, n squared over 2 to the n, converges to 0. Great. Oh, my eye just feels weird all of a sudden. Sorry. Okay. Yeah, let's look at that. Yeah, so this next one is kind of, this is the one that I was thinking of. And then I'm going to kind of, yeah, I can say that. So I want to look at this sequence. A sub n equal to n factorial over 4 to the n. Yeah. This one is tricky. It's definitely an infinity over infinity. So I should say, right, if I'm trying to take the limit, as n goes to infinity of n factorial over 4 to the n. I guess I should say, just to make sure everyone is clear, right? N factorial means n times n minus 1 times n minus 2 times every smaller integer until you get to 1. So for example, right, 5 factorial is just 5 times 4 times 3 times 2 times 1. That's what a factorial is, in case you haven't seen it before. And the problem with a factorial is, at least as far as we're concerned, it's not really a continuous function. It can't really be differentiated. So we are not able to use L'Hopital's rule whenever we're faced with a expression that has a factorial in it. So factorials automatically mean L'Hopital's rule is out, which means this is actually kind of challenging. So let's write out some of the terms. So if I start writing out the terms, I'm going to say that my a sub n terms are going to be, so if there's actually 2 other things I should say. 4 factorial is, 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. 1 factorial is 1. And 0 factorial, I don't think this will really come up in this class, but just in case it does, you should know that 0 factorial is defined to be 1. It's kind of similar to why like 3 to the 0th power equals 1. It's not exactly the same, but it's kind of the same in that other rules that we have all agreed on make it so that 3 to the 0 has to equal 1. Right? This is true because of the additive law of exponents. Right? We know that 3 squared times 3 to the 0, we get to add the exponents there and get 3 to the 2 plus 0. But that means this has to be 1 because 3 squared times 1 equals 3 squared. There are similar reasons at play that I don't really want to get too deeply into here, but there are reasons like this that make it so 0 factorial has to equal 1, otherwise the whole picture falls apart. It has to do with combinatorics, which I don't know where you guys see that. I don't think you see it in the 21 series, but eventually you might. Anyway, 0 factorial is 1. Don't worry too much about it. I want to start writing out some terms here. So I'm going to get 1 over 4. That's 1 factorial. So, and then my next term is going to be 2 over 16, right? 2 over 4 squared. And then my next term is going to be 3 factorial, which is 6 over 4 cubed, which is 64. So it looks like things are getting smaller. right? This is 1/4. This is 1/8. This is 3/16. Sorry, 3/32. And then the next one. So the next one actually is where we start to know something. If you have 4 factorial over 6 to the 4th, that's going to be 24 over, sorry, 4 to the 4th, not 6 to the 4th. 4 factorial is that. And 4 to the 4th is 4 times 64, which is 256. I didn't want to write that. Because what I want you to see here is that if I cancel a 4 here and the 4 here, it's actually the same as the previous term, which makes me think maybe things aren't always getting smaller, right? Got smaller, smaller, but then it stopped getting smaller. And if we write the next term, which is going to be 5 factorial over 4 to the 5th, what I'm essentially doing from the previous term, well, and this is kind of the nice thing about factorials, you get the next one just by multiplying by the next number. So if you have 4 factorial, you can get to 5 factorial just by multiplying 4 factorial by 5. So 5 factorial is really 5 times 4 factorial. And 4 to the 5th is really 4 times 4 to the 4th. So look, I took my previous term, 4 factorial over 4 to the 4th, and I multiplied it by a number that was bigger than 1. And then my next term is going to be 6 factorial, which is going to multiply the top by 6 over 4 to the 6, which is going to multiply the bottom by 4. So the next term, 6 factorial over 4 to the 6th, is going to be 6 times the previous one over 4 times the previous one. So look, we multiplied again by a number that's bigger than 1, which means it got bigger. So after we get to the 4th term here, every other term actually gets larger, which makes me think this thing is probably divergent. So how do we show it? This one's always one that's a little bit challenging the first time around. So what people, I don't know, people often kind of just say it's getting bigger. You could do something like say, right, for, no, I don't know, like, I don't really actually know what the good way to say this is, right? So this is, so I guess you could say this is equal to 5/4 times a sub 4. This is equal to 6/4 times a sub 5. I'm trying to think of like a way to say this kind of very specifically. So I guess you could say that so this is, right, this is a sub 6, this is a sub 5. So it looks like if I was trying to write a kind of recursive relationship, I could say that, well, it looks like the nth term is equal to n over 4 times the previous term. I don't think you really need to do this. I'm just kind of thinking out loud here. So we can see that, oh, well, if I multiply by n over 4, as long as this is positive, it's going to get bigger. So it looks like the limit as n goes to infinity of a sub n is infinite because the top is larger. So here's something I think is worthwhile to keep in mind. In general, polynomials smaller than exponentials eventually smaller than factorials. And then the biggest thing which we usually encounter is n to the n. So polynomials, I'm thinking of something like n squared, n cubed, n to a power. That's always going to be less than an exponential, like 2 to the n, e to the n, 3 to the n. There's going to be less than the factorial, which is n factorial. That's going to be less than n to the n. So this is the order of things that get biggest fastest. Polynomials are kind of the slowest. Exponential is a little bit faster. Factorial is really fast. N to the n is super fast. And there's also slower things, right? There is just good old n by itself. And then there's fractional powers or roots, like n to the 1/2. And then there's, I ran out of room, logs, which is like, sorry, I hate when I run out of room. Natural log of n. So logs are kind of the slowest. Roots are also pretty slow, but faster than logs. Then those. So if you can keep this in mind, it helps us kind of figure out, oh, so let's say someone asked me, what's the limit as n goes to infinity of, I don't know. This could be kind of a dumb example. Maybe not. Of the square root of n over the natural log of n. We can still use L'Hopital's rule to figure it out, but we have a pretty good idea that since we know that root things are bigger than logarithmic things, since the bigger things on top, this limit should be infinite. And it is. I'm going to use L'Hopital's rule and say that the limit as n goes to infinity. The derivative of the top is 1 over 2 root n, or 1/2 times n to the negative 1/2. And the derivative of the bottom is 1 over n. I'm going to rewrite this. I'm going to flip and multiply and get the limit as n goes to infinity of 1 over 2 root n times n over 1. N over root n is the square root of n. So that's the limit as n goes to infinity of the square root of n over 2, which is infinity over 2, which is infinity. So keeping this in mind can be helpful in seeing what we think is going to happen with any of these. Time is it? Okay, we're class till 3. Yeah. Okay, I got a couple more. Let me ask you guys. I know I think in both people's classes, some of the problems where you have to like figure out the formula for the sequence. Like they give you the first 4 or 5 or 6 terms and they ask you to figure out the formula. Should we do some problems like that? Yes, please. Okay, great. I want to do 2 other problems first and then we'll do that. So one of them is very straightforward. So let's say our sequence is 1 plus 1 over n to the n. And I want to write out some of the first few terms. So I've got, let's see, a sub 1 is 1 plus 1 to the 1, which is just 2. A sub 2 is 1 plus 1/2, so 3 halves squared. A sub 3 is 1 plus 1/3, so 4 thirds cubed. A sub 4, it looks like the pattern is, right, the fraction just gets 1 bigger on the top and the bottom, and it does, right? This is n plus 1 over n. So it looks like we have something where the inside or the base is getting closer and closer to 1, which makes sense because 1 plus something that's smaller and smaller is going to get closer to 1. And the exponent is getting closer and closer to, or getting larger and larger. So how do we deal with this? Well, one of 2 ways. Some people, I would imagine many of your professors are probably like, you should just know that this is the limit of this is e, but you can also show it. So if someone asks you to find this limit, and this limit does pop up every once in a while. If you're trying to find the limit of 1 plus 1 over n to the n, you have to do the whole thing where you take e to the natural log and then use L'Hopital's rule. This is equal to the limit as n goes to infinity of e to the natural log of 1 plus 1 over n to the n. And then we bring the n down. So it's e to the n times the natural log of 1 plus 1 over n. And then we bring the n to the denominator of this exponent. So we write it as natural log of 1 plus 1 over n over the reciprocal of n, which is 1 over n. So it's the limit as n goes to infinity of e to the natural log of 1 plus 1 over n over 1 over n. And now we can use L'Hopital's rule because this exponent is going to the natural log of 1 plus 0, which is the natural log of 1, which is 0, over 1 over n, which is going to 0. So using L'Hopital's rule, we get the limit as n goes to infinity of e to the derivative of the top over the derivative of the bottom. All right, it's going to be a little bit messy here. So the derivative of the natural logarithm of stuff is 1 over the stuff. So 1 over 1 plus 1 over n times the derivative of the stuff. And the derivative of 1 plus 1 over n, well, the derivative of 1 is 0, and the derivative of 1 over n is negative 1 over n squared. Or the derivative of n to the negative first is negative 1 times n to the negative second. I like to write it as negative 1 over n squared. And the derivative of 1 over n is negative 1 over n squared. And we see that for this problem, those exactly just cancel out, which is great. So then we get e to the 1 over 1 plus 1 over n goes to 0. So we get e to the 1, which is just e. So that limits e, which means this sequence does converge. It converges to e. It's kind of neat. It definitely is something that will show up again and again. So you should definitely get used to seeing it. There's some cool series questions that use the ratio test that have that limit kind of pop up inside of it, which I think is kind of interesting. But let's look at some of the identifying the pattern kind of questions, which can be challenging. Where did you go? Sorry, one moment. There's kind of usually 2 or 3 or maybe 4 types of patterns that pop up in those types of questions. Yeah. So I'm going to grab the ones from Grant's page because they're right there for me. So this first one I think is not too bad. 7, negative 11, 15, negative 19, 23, negative 27. So first and foremost, if you see something that's alternating signs every other term, ignore that or account for it, right? So I know that the alternating part means I'm going to have a negative 1 to the n or n plus 1. It really depends on where you want to start. So do we want to start with n equals 1 or n equals 0? Let's say 1, but you can make whatever choice you want unless someone specifically says you need to start somewhere. So I start with n equals 1. When I plug in 1, I get negative 1 to the 1, which is negative. But I want my first term to be positive, so I actually need to make this negative 1 to the n plus 1 or n minus 1. Either way, if you add or subtract 1, you will change what you start on being negative to what you start on being positive. So we adjusted for the alternating part. So now we can completely ignore that. And ignoring that, here's what I see. I see 7, 11, 15, 19, 23, 27. I see a sequence where each term is 4 more than the previous term. So I'm going to take my starting number and just add 4 each time. So maybe that's not the best way to say that. If I want to add 4 each time, here's what I'm really thinking of. A sub n, the n, which is the index, that increases by 1 every time. Like a sub 1, a sub 2, a sub 3, a sub 4, et cetera, et cetera. If I've got something that increases by 1 every time, which is n, but I want this to increase by 4 every time, I take the thing that increases by 1 every time and I multiply it by 4. So I need a 4n. Now, if I just left it as 4n, my first term would be 4n, and then my next term would be negative, right? So if n is 1, I get 4. If n is 2, I get 8. If n is 3, I get 12. If n is 4, I get 16. But I don't actually want to get 4 for my first term. I want to get 7. So if I plug in 1, I'm going to get 4, and I need to add 3. And now that looks right on. If n is 1, I get positive 7. If n is 2, I get negative, right? Because it's negative 1 to the third power, which is negative. And I get 8 plus 3, which is 11. So this 4n will up it by 4 every term. And I started at 7, so I'm good. And this n plus 1, or negative 1 to the n plus 1, will make sure it alternates signs every time. And so sometimes people say this, and then they write like something like n greater than or equal to 1 to show where they start. An equivalent but different answer would be to write a sub n equals negative 1 to the n, and write it as 4 n plus 7 starting at 0. That would be equally good. If I plug in 0, it starts off positive because negative 1 to the 0 is positive 1. And then 4 times 0 plus 7, it starts with 7. I usually just check my first term because if I know the other part's right. But then the next term, I have n equals 1 now. I get negative 1 to the 1, which is negative 1, times 4 plus 7, which is 11. So I get negative 11, which is my second term. So there's actually technically an infinite number of ways you could write a sequence like this or find the formula. But usually there's only two ways we typically look for, either starting at n equals 1 or starting at n equals 0. It's been a while since I've talked so much. I've had 2 weeks of not talking a lot, so my voice is a little tired. Let's do a couple more examples. So one thing to look for in your sequence is if you have something that is increasing by the same amount each time. So if you're increasing by some constant each time, you're usually going to have n times that constant. Let's look at this next example. So these examples feel maybe a little too easy, but let's look at this one. I'm going to try and make some harder ones. Let's look at this one. 3/5, 4/9, 5/13, and 6/17. And so this one, usually when we see these problems, we typically think of the numerator and the denominator separately because they're often written that way. So for the numerator, I see that the terms are increasing by 1 every time. So for my pattern, I probably want something like n. Okay, where are we starting at? N equals 1 or n equals 0? I don't care. Somebody write a number. Anybody? Great, 1. We're starting at 1. So I'm starting at 1. I'm going to plug in 1 for n and then add whatever I need to make sure that the first term is what I want to start with on top. So since I'm starting at 1, I'm going to do n plus 2. So that my first term gives me 3 when I plug in n equals 1. If I was starting at 0, I'd plug in n, I'd write n plus 3 on top. Okay, the denominator is a little bit more work. Looks like every time we're increasing by 4. So I know I want the bottom to have a 4n, because that'll mean every time n increases by 1, the bottom will increase by 4. But I don't just want 4n. I want when I plug in n equals 1 to get 5. When I plug in 1, I get 4 times 1, which is 4. So I have to add another 1 there. And now that should work. Because now when n is 1, I get 5. When n is 2, I get 8 plus 1, which is 9. Yep, we're looking good. So this will ensure that we increase by 4. This will ensure that we increase by 1 each term. And then the plus 2 and the plus 1 are just to make sure that we start off in the right place. Okay, but they definitely can be more complicated. There are typically 2 other types of ways of increasing that show up, I think, on occasion. So let's look at this next one. Yeah. There's also that 12, -4, 4/3, 4/9. Oh, sorry, -4/9. This one does not look super obvious to me. Yeah, how do you say this? Well, so we certainly have the alternating part. So I know I'm going to have a -1 to the, let's say we're going to start at n equals 0 here. Just so I can write a -1 to the n. We're going to start at n be greater than 0. Now, here, right, it looks kind of funky. I see my denominator. Like I can write this as -4 for 1. I can write this as 12 for 1. It doesn't really help me kind of do what I did previously, right? The top doesn't have any kind of, it's not like we are adding or subtracting anything because these are all 4s. The bottom also kind of confusing. Here, so if you don't see anything that's like increasing or decreasing in the same sort of way, you might want to start looking to see if maybe you're multiplying by the same thing each time. And that is actually what's happening here. 12 divided by 3 is 4. 4 divided by 3 is 4/3. 4/3 divided by 3 is 4/9. Or another thing that is 12 times 1/3 is 4. 4 times 1/3 is 4/3. 4/3 times 1/3 is 4/9. So here, every time we're multiplying by another 1/3. So we need a 1/3 to the n to account for every time we're going to multiply 1/3. Now, this doesn't quite get me there. So if I plug in n equals 0, I get 1 times 1, which is 1. But I wanted to get 12. And now it's going to work. Because when I plug in 0, I get 12. And then when I increase n by 1, I'm going to multiply by a 1/3 n by a -1. So when I plug in n equals 1, I'm going to get 12 times 1/3 times -1, which is going to be -4. When I plug in n equals 2, I'm going to get 12 times 1/3 squared, which will be 12 times 1/3, which is 4, times another 1/3, which is 4/3, times a -1 squared, which is still going to be positive. I could probably write this slightly simpler. I could probably write this as either 12 times -1/3 to the n, or if I wanted to go as compact as possible, I could even write it as 12 over -3 to the n. That would also work. But I feel like this is probably, I think this is kind of nicer because it shows, it's more typical of how you would actually write this. Now, let me actually take a quick look at this homework assignment just to see if there are any ones like that. Yeah, cool. Okay, good. So I'm seeing, yeah, let's do one like that. So I'm gonna modify this problem I'm seeing from Waldron's homework just slightly because it looks tricky, and I think the way I want it to be, yeah, it is. Okay, so here is the pattern. Let's say it's 3 over 2, 6 over 6, 9 over, sorry, brain work, 9 over 12, 12 over 20, 15 over 30. So here's an issue. So I've written this in a very nice way. I know it might not look that way, but here is a much worse way someone could write this if they were not kind. Maybe not, maybe, no, maybe, So sometimes, I'm seeing for myself here, it pays to, so maybe I did something dumb. Did I do something dumb? I guess maybe I did. I'm reducing these fractions, and I'm seeing if I divide this by 4, no, I guess 3/5. Sorry. I was reducing this. I reduced this fraction. Am I getting, yeah, what the heck? And maybe I adjusted this problem in a way that was dumb. I'm going to change it back to the, I was trying not to do one of the homework problems because, yeah. But let's actually write down the one that he wrote because maybe there's a reason. Or maybe not. Maybe I'm just silly. I thought I was seeing something kind of weird, but maybe I'm a liar. So this is the actual problem that is written. But maybe it's just as nice. So sometimes, most of the time, in my experience, but maybe my experience is not right, most of the time when people write fractions that are unreduced, it's meant to be helpful because it's supposed to allow you to see the underlying pattern that's there. But in this case, I think it's actually obscuring the pattern because if we reduce each of these, this is 2 or 2 over 1. 8 over 6 reduces to 4/3. 12 over 12 reduces to 1. 16 over 20 reduces to 3/4. And 20 over 30 reduces to 2/3. Is that helpful? I mean, it looks like it. So what's the next? It's a weird problem. I don't know. I don't know if this helps or not. I thought it was going to help. I'm curious. What do you guys think the next term would be? I feel like it has to be 1/2. Well, here's what I'm seeing from this. The top is getting bigger by 4 each time. The bottom is getting bigger by 2 more each time. Sorry, so this increased by 4, by 6, by 8, by 10. So it should be by 12. 24 over 42 doesn't reduce to 1/2. It reduces to, those are both, those are by 2. 12, 21st, those are by 3, so 4/7. That doesn't look like it follows any sort of pattern. Am I dumb? I might be dumb. Sometimes I make dumb mistakes. Yeah, 16 over 20. It's not 15 over 20. It's definitely 4/3, which definitely helps me see that there's not this. Wow, 4/5. Oh no, that does help see the pattern. Interesting. So this to me, so here's how I'm going to write things. I'm going to leave this as 4 seconds, 4/3, 4/4, 4/5, 4/6, 4/7. So that's what's happening there. That's kind of tricky. So it looks like the pattern would be 4 over n plus 1, where we're starting at 1. That's a little, so I was mistaken in that you don't, so I will say once again, often things are written in the non-reduced way because it's meant to be helpful. Here it was meant to be hiding something. So you should think about, is reducing the fractions helpful? But maybe not, reducing them all the way wasn't maybe super helpful. But, and also reducing them wrong is definitely not helpful. Yeah, I'm really curious because there are other patterns that pop up. Yeah, okay, so for example, let me just throw 2 quick ones at you guys. So there's one kind of like this in the notes, which is not going to be super hard. Let's say we had this, yeah. So we've got 5, -5 over 4, +5 over 9, -5 over 16, +5 over 25, which someone could write as 1/5 if they were trying to be cruel. So clearly it's alternating. It certainly looks like the top is 5 every time. So I'm thinking I have something like a -1 to the n plus 1 if I'm going to start at n equal to 1. And then it looks like the top is just 5. All right, this is 5 over 1. And this here doesn't follow the pattern unless I rewrite it. Right? So sometimes people, on the other hand, will reduce things to make it more confusing. Not usually, but it's something to be aware of. This is really 5 over 25. So now we can see the top is just alternating 5s. And the numerator, what are those numbers? 1, 4, 9, 16, 25. Oh, they're square numbers. So that is something else that comes up quite frequently, is square numbers. And I don't see anything like this. I know we're out of time, but I just want to point out that sometimes people write things. So let me give you one more, even though it's 3 o'clock. You're welcome to leave if you need to leave. But let me just shoot one more at you here, and then we'll call it a day. Let's say our pattern was this. Let's say we had, sure. Sorry, I'm trying to make up something not too terrible. Let's say it's 6 over 3 Sure. 12 over 6, which I know feels dumb. 24 over 11. 48 over 18. And 96 over 27. Sure, we'll do one more even. 192 over 38. Now, again, I will mention, if someone was trying to make this harder, they might write this as 2, 2, so on. I don't really think that's going to happen, but just be aware. But looking at this as it's intended, where the fractions, the top and the bottom are kind of doing totally different things, what's happening to the top each time? 6, 12, 24, 48, 96, 192. We're clearly doing what? We're definitely doubling. Yeah, multiplying by 2. So when we're multiplying by 2 each time, that means the first time we're going to times by a 2. And the second time we're going to times by a 2 and then another 2. So each time we have to multiply by another factor of 2, meaning we need a 2 to the nth power. So I need a 2 to the n. And then I need, for my first term, to be 6. So I need a 3 times 2 to the n. So that when n is 1, I get 3 times 2, which is 6. And when n is 2, I get 3 times 2 squared, which is 12. And when n is 3, I get 3 times 2 cubed, which is 3 times 8, which is 24. So if you're multiplying by 2 every time, you need that number 2 to the nth power. So that every time you get another multiple of 2, increasing your thing. Now, the denominator might be harder to see. 3, 6, 11, 18, 27, 38. That doesn't look like any pattern I'm aware of. What it is it's the squares, but multiplied or added by 2. So here's the way I often think about the squares. If you've got numbers that are following an n squared pattern, which is why I thought this previous problem was kind of an n squared pattern, I tricked myself into thinking it was, is when you have a square pattern, the way these increase are always in this odd way. In fact, the way I really kind of think about it is, if you look at how the parts that increase, which I know I'm writing over myself here, it's a constant, which if you think about derivatives makes a lot of sense. If your function was x squared, its rate of change is 2x, or its derivative is 2x, and that rate of change is the derivative of 2x, which is just 2. So every time the change of the change is 2, I'm thinking, oh, it's probably something squared. I know it's kind of funky sounding, but that's really what I'm thinking about. So for this one, I see that my changes again are 3, 5, 7, 9, 11. When you have that odd difference increasing power, right, where the first one's 3, then 5, or the first one's odd number, the next one's the next odd number, then the next odd, and the next odd, that means you've got something squared. So I've probably got something like n squared, but I want to start at 3, so I need n squared plus 2. That used to come up kind of often, I feel like, with these questions, but maybe that's less of a thing now. Anyway, it's something to be aware of. All right, that is more than all the time we have for today.